Voyager 1 has been traveling for 18 months. It has crossed the asteroid belt, survived the radiation fields around Jupiter, and is now sending back the closest images of the Jovian moons ever captured by a human instrument. One of those moons stops the team cold. Europa is small, roughly the size of our moon. From a distance, it looks like a cue ball. No mountains, no deep craters, almost smooth. But as the images sharpen, the team notices something that doesn't fit. The surface is covered in lines, long, rust-colored cracks running thousands of kilometers across the ice, organized fractures. Astronomer Lawrence Soderblom looks at the data in real time, describing the surface as resembling a cracked eggshell. What he means, though he doesn't say it directly, is this. For a surface to look like this, the ice beneath those cracks has to be moving, floating on something. The team files it away. It's a striking observation, but they have no way to explain it yet. Voyager 1 is already past Jupiter and heading towards Saturn. They can't go back. And it's going to take another 16 years before anyone does. The Galileo spacecraft reaches Jupiter on December 7, 1995. Its mission is to study the Jovian system up close. The planet, the moons, the magnetosphere. Scientists have their list of things they expect to find. Europa is on the list, but it isn't the priority. Then the magnetometer data comes back. Margaret Kivelson is a plasma physicist at UCLA. She's part of the team analyzing Galileo's magnetic field measurements. What she's looking at doesn't make sense at first. Europa has a magnetic field, but it's fluctuating. It changes depending on where Europa is in its orbit around Jupiter. It responds to Jupiter's own field, like a conductor reacting to an external current. There is one known mechanism that produces that signature: saltwater, conducting electricity, moving beneath Europa's ice. Kivelson and her team published the results in 2000. The conclusion: Europa almost certainly has a global saltwater ocean beneath its ice shell, somewhere between 10 and 30 kilometers below the surface. At this point, the question isn't really whether the ocean exists. The question is why it's still liquid, because by every measure, it shouldn't be. Europa sits about 628 million kilometers from the Sun. At that distance, solar energy is roughly 25 times weaker than it is on Earth. The surface temperature is around -160 Celsius. An ocean at that distance should be completely frozen. Solid ice all the way down. So why isn't it? The answer is Jupiter. Jupiter is so massive that its gravity doesn't just hold Europa in orbit, it physically deforms it. Europa's orbit is slightly elliptical, so the gravitational pull it experiences isn't constant. When it's closer, Jupiter pulls harder. When it's farther, less so. The moon literally flexes, stretches, and compresses on every single orbit. That flexing generates friction, which generates heat, and that heat, over billions of years, has kept the interior of Europa warm enough to maintain a liquid ocean. This process is called tidal heating, and it completely breaks the conventional idea of what makes a planet or moon habitable. For decades, scientists defined the habitable zone as the narrow band around a star where liquid water could exist on a surface. Too close, too hot, too far, too cold. Earth sits comfortably inside it. But Europa is nowhere near that zone, and it has more liquid water than Earth, which means the habitable zone concept, as a filter for finding life, might be basically useless. You don't need to be close to a star, you just need to be near something massive enough to heat you. This single idea expands the number of potentially life-bearing worlds in the universe by an order of magnitude. Before we get to whether anything is living in Europa's ocean, we need to talk about a dive that happened 2 years before Voyager reached Jupiter. February 1977. The research submersible Alvin descends to the Galapagos Rift, a section of the mid-ocean ridge roughly 2,500 meters below the Pacific. A team of geologists are looking for hydrothermal vents, cracks in the seafloor where seawater seeps into the crust, gets superheated by the rock beneath and comes back out. Their mission is to map them. When they get there, the team finds the vents. But around them, clustered so densely the lights of the submersible can barely take it all in, is life. Tube worms 2 meters long, pale crabs, mats of bacteria covering every surface, an entire functioning ecosystem at crushing depth in complete darkness without a single ray of sunlight reaching it. Before that dive, the scientific consensus was that sunlight was a prerequisite for life. Alvin dismantled that in one afternoon. The reason this matters for Europa is direct. If Europa's ocean floor has hydrothermal vents, which tidal heating makes likely, then the same chemistry that powers life at the bottom of our oceans would be available at the bottom of Europa's in permanent darkness, beneath 30 kilometers of ice, 600 million kilometers from the sun. There's also a second chemical mechanism at play. Jupiter constantly bombards Europa's surface with radiation, far more than Earth receives. That radiation breaks apart molecules in the ice and creates highly reactive compounds called oxidants. When sections of the ice shell eventually fracture and sink back into the ocean below, those oxidants go with them, becoming available for chemical reactions in the water. Reactions that could, in theory, sustain biology. In other words, the radiation that makes Europa's surface completely hostile to life might be actively fueling the ecosystem underneath it. Lawrence Roth is a planetary scientist at the Southwest Research Institute. In late 2012, he's working through ultraviolet data from the Hubble Space Telescope, routine monitoring work on Europa. The data shows a faint emission near Europa's south pole. He checks it again. It's there, a plume, water vapor, shooting roughly 200 kilometers above the surface into space. This is a significant problem. The prevailing assumption was that Europa's ocean was sealed, completely enclosed by ice, with no way in or out. That made it geologically interesting, but logistically impossible, because to sample that ocean, you'd have to drill through up to 30 kilometers of ice. But a plume changes everything. If Europa is periodically venting ocean material directly into space, a spacecraft doesn't need to drill through anything. It just needs to fly through the plume. The ocean comes to the spacecraft. Roth and his team published the results in December 2013. The reaction is cautious. Hubble only saw the plume once. But in 2016, Hubble sees it again, a different location, similar scale. 1 year later, researchers re-examining old Galileo data find a magnetic anomaly consistent with a plume that the spacecraft may have inadvertently flown through in 1997, before anyone knew to look for it. The plumes aren't consistent. They come and go. They're likely tied to specific points in Europa's orbit, moments when the tidal forces from Jupiter are at their strongest, cracking the ice just enough to let the ocean exhale. The same force that keeps the ocean liquid also opens a window to it. The Europa Clipper launched on October 14, 2024, on a SpaceX Falcon Heavy rocket. It's the largest planetary science spacecraft NASA has ever built. The main body is about the size of a basketball court when the solar panels are deployed. Right now, it's already in transit. It won't orbit Europa directly. The radiation environment that close to Jupiter would destroy the electronics within a few months. Instead, it will perform 49 targeted flybys over the course of its mission, dipping in to gather data and pulling back before the damage accumulates. The instruments include ice-penetrating radar that can see through the shell and map the ocean beneath it, a mass spectrometer to analyze whatever it finds in the plumes, a magnetometer to precisely measure the salinity and depth of the ocean, and cameras capable of resolving surface features less than a meter across. Europa Clipper reaches Jupiter in April 2030, and its primary mission runs through 2034. But Europa isn't even the only one. Enceladus is already venting ocean water into space. We flew a spacecraft through it in 2005 and found organic compounds. Ganymede has a subsurface ocean, so might Titan and Callisto. That's 5 moons in our solar system alone, and we've barely looked. The Milky Way has somewhere between 100 and 400 billion stars. Most have planets, which have moons. If tidal heating works here, it works everywhere. There's a gas giant, which is most of the galaxy. So either subsurface oceans are common and empty, or they're not. Europa Clipper will be the first real test of that question,